with just using the property temperature. But anyway, the temperature is very unique property, which is already, which is kind of rigorously kind of connected with the thermodynamics itself. So thermodynamic is very kind of, well tied to the temperature itself, so other than other dynamics or other physics or other mechanics. So anyway, so temperature is that, and also when defining the temperature, people just start. They just start with the George law of thermodynamics. Again, the George law of thermodynamics itself it sounds very trivial. So meaning, so if two systems are separately in thermal equilibrium, a third system. So in a given third system, and then if you have system A is in thermal equilibrium with this guy, and then you have in given same system, you have the separate system B, which in thermal equilibrium with this guy, and then without touching A and B, and then put them together, we know they are in thermal equilibrium with each other. And then to represent that fact, or to represent the thermal equilibrium, there should be some property of your substance which can describe the thermal equilibrium, and then people just assign that special function for the thermal equilibrium as temperature. So what that means is, in thermal equilibrium, what becomes the same between two separate systems, and then their temperature becomes the same when they're in thermal equilibrium. So temperature is the property which tells you the thermal equilibrium. Okay, so that was the kind of starting point of the temperature discussion from the direct law of thermodynamics, and then we've done some derivation, but I'm gonna skip it. So you just take a look at it by yourself, and then it'll be kind of obvious. And then again, the important thing out of all these kind of derivation is temperature is that special function which describes the thermal equilibrium, and then that property becomes the same when you have thermal equilibrium between any kind of thermodynamic system or substances. So that was the end of discussion of this lecture note. Any questions up to this point? 혹시 여기까지 궁금한 거 있어요? 없어요? 네, 오케이. 감사합니다. 오케이, 그러면은 넘어갑시다. Okay, then we start to talk about the equation of state. So once we've done talking about the thermodynamic properties in the previous slide, and some introduction and thermodynamic properties later on. And then so once we understand the thermodynamic properties, property of this pressure, volume, temperature, those, and then we can use those thermodynamic properties to define the thermodynamic state. So again, the thermodynamic is what's uniquely defined. And then once you're in a thermodynamic state, it doesn't matter, the energy of it, entropy of it, specific volume of it, Gibbs energy of it, what all the thermodynamic properties you don't know about certain thermodynamic state, but that doesn't matter. It's already determined, but you just don't know the value of them. Okay, so that's what the thermodynamic determination of thermodynamic state. So it could be given by any two independent thermodynamic properties, again for now, but in this lecture, we're going to talk about that soon. So how many thermodynamic properties we need to have to define the thermodynamic state. Again, once you're given, or once you're fixing the thermodynamic state, everything else are all known. You don't know the values of them, but still we know they are fixed already, and it's uniquely given. So, and then this equation of state here, again, so last time we were just talking about that, and then it was functional relationship. So it's a function, and then it gives you the functional relationship among the state variables. And then for equilibrium system, again, this is an important point. So we're not talking about non-equilibrium system and an equation of state for it. And it's about equilibrium system. And then typically, again, given in PVT relationship, because they are easily measurable. That's historically easily measurable as compared to the energy, entropy, or other things, which are indirectly measurable. but these are more or less directly measurable. So that is the equation of state, and then we just had a certain kind of examples of equation of state. The first kind is the ideal gas equation of state. Again, so if you have your real substance behaves like an ideal gas, again, there's no such thing ideal gas in real life. You have certain real gas which behaves like an ideal gas. Okay, so this is only the assumptions you're making. But let's say your gas behaves like an ideal gas, and then the condition for it is the density goes to 0, or specific volume, as you mentioned last time, goes to infinite. That's what's required for your real substance behaves like an ideal gas. And then only in that state, 잠깐만요. only in the state, 채팅창이 닫히셨네. only in the state, this condition, this functional relationship is satisfied. So your real gas will follow this PV and RT, so P and V and T relationship, only when it behaves like an ideal gas, or the density goes to 0, or specific volume goes to infinite. Okay, so that's ideal gas equation of state. Or you could be more realistic, and then for real gases, and then you could have, actually last time this was our starting point, and then we introduced the van der Waals equation of state. And then in this van der Waals equation of state, they try to incorporate some of the realistic properties of your real substance. And then there is a compressibility factor, again, that we've used last time. So as you can see, as given PV over RT is equal to Z instead of 1 in ideal gas equation of state. This was 1, but instead of that, it's using Z. And then Z, as you can see, is a function of, T and V, or P and T, or other two properties. So meaning Z is actually not 1 all the time. It's changing along the different thermodynamic states. And then this Z is tabulated for you. And then you can use that Z value in that PV over RT is equal to Z to evaluate, for example, V out of given P and T. So meaning in a given P and T, you find out your Z value for it, and then you can calculate V out of the equation. So Z actually makes your equation of state and copying with the real behavior of your real gases. Okay, so that's the compressibility factor. And then the last one, and this is not exactly the last one, I'm just listing up some of the examples. So called the virial equation of state. And then as you can see, again, it's a PV over RT still, and is equal to 1 if it behaves like an ideal gas, but it may not. So that's why they have this, T and M V, equations there. So meaning in a given T and V, you will be given those B, C, D, E, F values, which will give you the value on the left. Okay, so again, this right hand side, these function will give you the realistic behavior of a real substance. And then again, this is not the end of the list, and then you have so many kinds of different equation of state for your substance. So whenever you need any real gas treatment in your thermodynamic analysis, you may just go to Google and then try to find the right equation of state for you. And then you'll find, if you are lucky enough, and then you'll find whatever you want out of it. Okay? So any questions about this page? Okay, yeah, 감사합니다. Okay, so and then this was in the discussion about when we can apply the ideal gas. I mean, just ideal gas equation of state, when and that makes sense, or when that doesn't make any sense. And then in the end, and what we've done is, so we've looked at this left figure, which is left plot, which is the compressibility factor chart of air. Again, the compressibility factor was Z on this equation. So again, when the Z is equal to 1, and then your gas behaves like an ideal gas in that specific thermodynamic state. If it's out of 1, now you have real gas behavior. So But in typical engineering application, if you're not doing any kind of low temperature stuff, or you're not doing any kind of fluid, I mean, like a liquid phase, but if you're dealing with, for example, the combustion, or like the automobile engine, or just gas turbine power plant, and then those, typical just gas, and then the ambient temperature operation, your operating regime pretty much around, again, the last time I mentioned, pretty much regime of this red box in this compressibility factor chart. So meaning your pressure is more or less than 100 bar, 100 times of atmospheric pressure, and then your temperature is above the ambient, and then up to 1000, 2000 Kelvin. That's typical in combustion case. And then this region, as you can see, these plots shows you the value of Z on the y-axis, and then they are not going more than plus minus 5%. So meaning Z is only varying from plus minus 1.05. So meaning if you don't have the good information on Z, like this plot, you may just use 1 instead of exact value of Z, and then you still are okay, and then your prediction is kind of within plus minus 5% error, if that's acceptable for you. So, and also in the right figure, and then I'm showing you the TV diagram for real water. And then if you remember, in the TV diagram, there's a kind of vapor dome like that. And then you remember that on the right-hand side of the vapor dome, you have the superheated vapor, or 과열증기요. Superheated vapor you have. And then if you have superheated enough, or if your specific volume, which is your x-axis, if the specific volume is large enough, and in this, blue region you're seeing, and in this, inside this region, if you assume the ideal gas behavior of your water, real water, and then just using the PV over RT is equal to 1, you still has a less than 1% in predicting of volume out of PNT, or temperature out of PNV, or pressure out of VNT. So meaning that's that small error. So you have just lots of region you can assume ideal gas behavior for your real water. But as you can see, if you get close to the vapor dome, so meaning that now your vapor is getting close to the saturated state, which will become liquid kind of through the dome, meaning your vapor just now being dense enough. And then now they are not anymore ideal gas. And then you have now real gas, and then there are intermolecular potentials. And then you're seeing that kind of somewhat bigger error, like 17%, 50%, and then 8%. And then so you have those errors, meaning if you use the ideal gas equation of state for those thermodynamic state of your real water, and then you will be quite off. And then we don't need to talk about the liquid side, and then you will have a huge amount of error on that side. So this is kind of the applicability or non-applicability of your ideal gas equation of state. Okay, any questions up to this point? 혹시 질문 있으실까요? 예, 감사합니다. 네, 계속하죠. Okay, this was the kind of stopping point of last time. So we introduced the van der Waals equation of state. Again, this was it's not really first, but it was kind of the original and the first of its kind, and efforts of the scientist to give us the equation of state for the real gas, especially considering the liquid phase. So the van der Waals equation of state you can use it for the gaseous and the liquid phase, or meaning you can work with it around the vapor dome. That's possible. But again, the form itself, it looks like here in this equation. So as you can see, it's quite simple. So meaning, yeah, it's okay. I mean, it's very well working for certain gases or certain substances, but it's not really well working for certain other gases. So meaning there is certainly the limitation. This is just the model equation of state. It's not really the real behavior it can capture. I mean, every of that kind of real behavior it can capture. So there is a clear limitation, but still, it's a very good starting point, and then it gives us all the kind of physical meaning and an intuition, and what should be included in the equation of state to describe more realistic behavior. So that's that starting point, and it's important to understand that. Okay, so let's do that, and then you can just actually do the similar kind of analysis and a similar logical thinking for other equation of state. You can just kind of follow the whatever we are learning here for the van der Waals equation of state. Okay, so all right, so van der Waals equation of state, considering two things which were missing in the ideal gas equation of state, and then I emphasized that last time, and then that was the size of the molecule. Again, in the ideal gas-like situation, your particles is much separated enough, and this vacancy are very large as compared to the whatever space the particles are really residing in. So meaning if you neglect the size of the particle in your volume calculation, that doesn't give you much error. Or in the ideal gas limit, because your specific volume goes to infinite, meaning they are totally negligible and there's no error associated with that. But now if you have condensed phase like the liquid, molecules are not that much separated. Actually, they are now becomes much more closer to each other. Now the vacancy is comparable, or you better include that volume of that molecule's taking in your equation or the volume itself. So meaning if you neglect that kind of size of the molecules in your condensed phase like liquid, and then you have kind of huge errors in it. So that's the one thing. So the size of the molecule you're going to consider. And then the second thing is the cohesive forces between molecules. Again, there are two forces, between the molecules. And then actually I just, have this website for you. Okay, so I'm gonna cancel it. Okay, so okay, good. Okay, is it here? Okay. Oh, so if you see this figure, and then this shows you the typical Lennard-Jones potential. So this is the typical potential between two particles. So when the particles are separated enough, and then your potential energy is this shape, and this is the kind of this. Okay, let me draw here. This is a distance between your two particle. So they are separated well enough on this side. And then in that case, your potential energy, as you get closer, and then your potential energy decreases. And if you remember, if in equilibrium, your energy will decrease to the equilibrium point. So this is in this way, actually, you're getting into the equilibrium point. But anyway, so this is the potential energy between these two particles. And if the potential energy is reducing as you reduce the distance between those two, there is a attractive force because your intermolecular force is given by minus of dpdr. dpd, I use a d, but that's confusing, is dpdr. So let's say it's r. Yeah. So meaning you're now having in this attractive force in this region. But once you get close enough, now you're at the wall of the potential energy. And then if you try to go beyond the point, meaning get closer than that, then as you can see now, the potential energy increases as you get it closer, get them closer together. And in this case, your force becomes repulsive. So meaning it's attractive in the beginning, but if it's close enough, now it becomes repulsive. And then that repulsive force, you can see that the slope is very strong, and then it want to just kind of push that out. It's like the molecule collide themselves, and then bounce it off. right away. This is that, potential energy plot, and then the force associated with it. Anyway, so there are, attractive force when they are far enough, and then if they're, close enough, now they just have the repulsive force. That's what typically happening. 잠시 오케이. 넘겨졌네. 그리고 그리고 가시죠. Okay, so 이게 참 이 컴퓨터가 이렇게 힘들어하네요. 역시 너무 많은 걸 시키면 안 돼. 잠시만요. 예. 오케이. 그리고 이 필기하는 컴퓨터는 왜 이렇게 자꾸만 프리즈가 나는지 모르겠네. 뭐 이렇게 대단한 걸 시켰다고. 제가 너무 웹사이트 하나 보여줬다고 이렇게 된다니. 예, 또 다시 저는 제 핸드폰으로 가야 되겠네요. 너무한다. 자, 들어가겠습니다. 잠시만요. 미안합니다. 이거 참. 오늘은 안 그러나 했더니 오전엔 괜찮았는데. 자, 봅시다. Okay, so cohesive forces between molecules, that's the second thing we are considering. So attractive force only. So we're not talking about the repulsive force. So then, and then this van der Waals equation, that means we have additional two terms. And as compared to the ideal gas equation of state, as you can see, we have this first term over there, and then we have the second term over there. So we have two additional terms, and then this first term is about the cohesive forces, so attractive forces. It's included here. I'm going to explain more detail. And then this second term is considering that finite size of the molecule in the condensed kind of phase, and which should contribute to the volume of your substance. So that's what it is. So as you can see, it's saying is pressure reduction by that attractive forces. So meaning, so how the pressure come up? I mean, just what is the pressure against the wall? So if you measure the pressure in the wall and then there's gas here, what is the pressure you're feeling here? Do you know that? What is that pressure coming from? 혹시 압력이 어떻게 나오는지 아세요? 이 가스가 있을 때? Very good. Yes, that's right. So particles will collide into the wall and then bouncing back. So colliding into the wall and bouncing back. And then if you're the wall, and then you feel that, impact, right? Which is actually the impulse, right? That's the momentum change of that particle. So you're going to feel that impulse on the wall, and then you divide by area of that impulse will give you the pressure. That's the pressure. Okay, so then if you have real gas, and then again the whatever the particle near the wall try to hit the wall and then coming back, and then that's the pressure. And then why it's reduced when there is attractive force is this. I mean, it's all qualitative and then this kind of intuitive thing. So meaning, so if you're a particle here trying to, approach the wall, but this one, 이거 참, 이거 좀 쓰면, 그리면 딱 좋은데. 뭐 제스처로만 할 수도 없고. 꺼지지도 않네. 참, 나오는데. 네. 어떻게 하지? 꺼지지도 않아요? 분명하겠네요. Okay, so let's try here. All right, so if you're in the wall and then particles here trying to go there, but you have other particles there, and then what they're effectively doing, they are pulling this guy to that side because there is attractive force. Is that right? So meaning this is, let's say this is the last, there's no such thing, but this is the last layer which will collide the wall in the next moment. And then the particle and that layer which was which was kind of going toward that wall, actually they're pulling back by the particles behind. And then so that means that will reduce the pressure by having that attractive force. That's the factor. And then that's why I say it's pressure reduction. And then there are actually two factors there. The first one is, so if you have, so it depends on how many kind of molecules you have near that the last particle. So meaning that corresponds to the density. So if you have a large amount, if you have big enough density, you have many particles behind and trying to pull you back. So that's the first one. And then the second one is how close they are. And then that also, somewhat related to your density. So those are actually twice or multiplication of effect of that density, and which will effectively reduce the pressure exerted by that particles colliding the wall. So again, I'm just giving you just very, qualitative understanding out of it, but that's actually how they just explain it. So anyway, so it's only approximate, and this is the model, and then that's why we have, instead of just 1/v, now we have 1/v squared. So you have multiplication of that effect of the density. Again, the 1/v is your density, so that's why it's just 1/v squared. Okay, and then the second part is the finite volume occupied by the molecule. So meaning, your real volume. So you understand this in this way. So let's say there's no intermolecular forces. So meaning, let's say you don't have that, and then you just have pressure being ideal. Okay, and then what you can do is you can just divide by it over there, right? And then what you have in the end is V real minus B is equal to RT over P real, P ideal. What is the right hand side? RT over P ideal. What is that? It's V ideal. Okay, it's V ideal. Yeah, very good. It's V ideal. So meaning your V ideal doesn't account for the size of your molecule. It only accounts for the whatever vacancies, because in a size of molecule, they are negligible. It takes a negligible volume, so you disregard it. But now you're seeing that the V real is the V ideal plus B. Okay, so now you are including that finite volume of your particle. Okay, so B represent the effective volume where the particles reside in, or it's this effective volume of your particles inside the system, basically. Okay, so does it make sense? 이해가세요? 예, 좋습니다. 당연히요. Okay, so that's that. 예. And then, so you can rearrange this equation and then down to this equation. And then because you have the v 1 over v squared there, and then there's a v there, so your final equation is and the v to the third power, and then that's why it's called cubic equation of state. It's cubic equation, with respect to the volume, specific volume. So that's the cubic equation of state. That's another name for the van der Waals equation of state. Okay, so and then once you draw the PV diagram for the van der Waals equation of state, and then you can set certain t in that equation, and then you can draw the PV diagram along that constant t, certain some number t, or that's basically your isothermal lines, right? It's an isothermal lines you're gonna draw, and then once you draw it, that looks like on your right hand side here. Okay, and then so as you can see, it has kind of multiple shapes you'll follow. Okay, actually that's more we have more detail on the next slide. So let me just move on to the next slide. But anyway, so before I move on, let me point it out that, and as you can see, this is the water's PV diagram here. This is the water's PV diagram. And then this is the vapor dome we mentioned. And then as you can see, these are all isothermal lines there. And then you have this like shape, and then you have this like shape, and then under the vapor dome there's phase change, and then is steeper in the liquid side, and then somewhat less steep, or is smooth. I mean, it's not steep, let's say, and then it's the vapor side. So you have this like characteristic of isothermal lines, which actually very well or approximately captured in this PV diagram, which is for the van der Waals equation of state. So you have this monotonic lines there, like this line over there, and then you also have this specific line which have this this is what is called? 변곡점이 뭐라 그러지? 다음 장에 써 있었던 것 같아. Inflection. Okay, so you have this inflection point in this plot, and which look like this inflection point on this real water case. So you have that curve included, and then under that point you have this like cubic equation of behavior. You have this like the minimum and then the maximum values around it. Anyway, so and then if you just cut that over there and cut that over there, that resembles whatever the liquid and then a vapor line when there is phase change. So meaning this simple equation, this cubic equation of state, actually has very similar shape of the real substances, including the vapor and liquid phases and unsaturated state. So to be more exact, or for more detail, so for isotherms, again isothermal lines, if temperature is high enough then and larger than the Tc, again the Tc, that whenever you see the C, that's your critical point. You know the critical point, right? 임계점 아시죠? 임계점. 임계점 잘 모르네. 오케이. 예, 아시는 분도 계시고. Okay, so if you remember which plot? Okay, let's just draw the P. Okay, so let's do it on the new. Okay, on the whiteboard. Okay, let's do it. Okay, PV diagram you're talking about. Okay, so let's start with this easy one. For ideal gas like state. So if you have an ideal gas, what is the isothermal lines will look like? It'll gonna go, positive slope or negative slope. Again, PV diagram, isothermal lines for your ideal gas. Do not think about any phase change yet. Is that having positive slope or negative slope? in the constant temperature process. Okay, yes, very good. So you have this like shape. You have this like shape, right? That's your isothermal lines. Okay. And then, but if you have phase change in PV diagram, your vapor dome look like this. Okay. And then, so this is a vapor dome. Let me ask you a couple of questions. Okay. So phase change in a given temperature that occurs at constant pressure. So phase change at constant temperature means you have constant pressure. Is that right? So water boils at 100 degrees Celsius at 1 atm. So at constant pressure, you always have the boiling temperature at 100 degrees Celsius, right? 맞죠? 상변화했을 때는 그 온도 변화도 없고 압력 변화도 없는 거죠. 네, 정확히 말하면 압력 변화가 없으면 온도 변화가 없고 온도 변화가 없으면 압력 변화가 없는 거죠. 상변화할 때. 그죠? Okay. So that's your phase changing line over here. So what is this state? What is it called? What is this phase, I should say? What is this phase? What is it called? Okay, that's a liquid. Yes, that's correct. It's saturated liquid. 포화액이죠, 포화액, saturated liquid. And then what is this guy? Okay, very good. That's saturated vapor. So that's what you have. Meaning now you have the vapor phase on this side. This is your vapor side. And then this is your liquid side. That's what you have. And then in the vapor side and liquid side, and then isothermal lines look like this. They still have negative slope. And then it has somewhat different kind of slope. And then as you know, in liquid phase over there, the volume will not change in your liquid phase, even if you change the pressure. So even if you just do the pressurization of your liquid, even if you increase the pressure hugely, but the volume will not change that much. That's why it has a high slope. But in a gaseous state here, it's a different story. So once you try to increase the pressure, volume also shrinks a lot. So that's why it has a somewhat kind of low slope in this PV diagram. So that's that, isothermal lines when there is phase change. Okay, let me ask you this question. What is this point over there? What is this point? Yellow. Okay, you remember? Very good. So that's your critical point. 임계점이죠. Critical point. Meaning up to that point, so below that pressure, so let's say this is the critical pressure. Below that pressure, if you do the boiling, you always have two phase. So meaning if you boil at this pressure, and then you have liquid and then vapor at the point, and also if you have this pressure of your boiling, and then you have the saturated liquid and saturated vapor when you do the phase change. But once you get up that pressure and also certain temperature corresponding to that, during your phase change, if there is phase change, during your phase change, and there's really no two phases you're gonna observe. Meaning your phase change look like this. You're going this way, and then you just have inflection and going that way. Meaning you just kind of just stays there, and then it seems like there's a phase change, but it doesn't really shows you the two phase. The two phase, what I mean by two phase, there's a clear phase boundary. For example, if you have the liquid and then a vapor at the same time, you always see the clear phase boundary in between. But in this specific yellow case, and in this yellow case, the temperature is your critical temperature. And then in this specific case, when it goes through that dot point over there, there's nothing really changed. Okay? It just goes through the point and then going into the other direction. Okay? That's what it is. So meaning if you go over in the isothermal line, if you go over the TC, or if you have higher, so for example, this, the first line we draw, this blue line we draw, it's actually greater than TC. This temperature is greater than TC. And then there, you don't have any phase change. But once you just touched on that critical temperature, you have that inflection going on. And if you go below the critical temperature, now you're clearly see the two phase in your phase transition. Okay. So these are the different, isotherms when you have a phase change. Any questions about this guy? 혹시 여기 질문 있어요? So I'm gonna show you some kind of movie later on, and then that's just it's not liquid, it's not vapor. We just kind of call that as supercritical fluid, which it just gonna become the single phase. So whenever you say liquid and then gas, you imagine something, but it doesn't need to be. I mean, just the liquid. So for example, this is the case. Why there is such thing like the critical point here? Because as you follow this side of the saturated liquid, as you can see, your saturated liquid specific volume becomes larger and larger, right? Meaning your liquid try to expand. That's what it is. I mean, that's the typical characteristic of your pure substance. And then from the from the vapor side, as you go up in pressure, now you're compressing your gas and then close together, and then its specific volume is getting smaller and smaller from vapor side. And then you say it's vapor, but it's more likely very close to the liquid. And at a certain point of time, which is your critical point, at a certain point of time, it doesn't matter you're talking about the liquid, it doesn't matter you're talking about the vapor. They are just pretty much in density-wise, pretty much the same. And then above that critical point, and then there's no more separation of such phases. That's what it is. So you're not saying it's not liquid, it's not vapor, but it's just kind of single phase. So a single phase, and then in this single phase, and then up this point, it's more like liquid. Down here at this point, it's more like a vapor. At this point, it just kind of becomes something intermediate. Okay, but it's not really it's not that. It's just kind of a single certain phase having certain thermodynamic state. That's what it is. 뭐 좀 대답이 됐어요? Yeah. Okay, other question? Okay, if not, well, let's clean this up. And then, not this one. Okay, let's go this way. All right then. Now you can understand this figure of the van der Waals equation of state. So if you draw your cubic equation on this PV diagram in a given T, so if you draw multiple isotherms like that, and then if you draw one with the temperature as much greater than Tc, that's this guy over here, okay? That's your first guy, okay? It's more likely, I mean, it's very close to the shape of the ideal gas equation of state, okay? And then if you still greater than critical temperature, but still not that kind of far enough, so meaning you're now getting closer to that critical temperature, then your shape look like this, the second one, and then still there's no inflection point yet. You're still over the critical temperature. But now if you just set it on the critical temperature, as you've seen, you now have the inflection point, and then that inflection point is at critical point of your substance. So, I mean, that's where you actually adjust those variables, parameters of your equation of van der Waals equation of state for your certain substance. So you're gonna just change your parameters in the van der Waals equation of state to match up that critical point in your real substance. And then if you go below that critical point temperature, now your van der Waals equation of state, it doesn't show you that real behavior. So it doesn't show you that real behavior like that straight line and then, during the phase change and then going down. It's not going to do that because this is a polynomial. If continuous just continuous function, definitely this kink will not going to happen. Instead, what it has is it has this kind of minimum and then a maximum. It's like the kind of cubic function, typical cubic function you're going to have. That's what happened. So there's a local maximum and a minimum. And then that means, you need to find out where that straight line should locate it in that, the smooth curve. That's what you're going to do in the next slide. Okay, so first thing first, so how to determine, I just mentioned it earlier, so how to determine the characteristic coefficient of the van der Waals equation of state. And then the characteristic equation, actually I didn't mention in the previous slide, right? Okay, the characteristic equation is your A and then B in the van der Waals equation of state, so you need to determine two and those variables. And then how you do it, actually you're using the critical point, meaning because once you know your substance, and we're going to talk about in the next slide, and then your critical point is a unique point for your substance. So meaning it's known to you once you know your substance. So meaning we're going to use that critical point, condition of thermodynamic properties, and then by using this. So because it has an inflection at critical point, remember we have this inflection on critical point, what you can have, this is the condition to have that inflection. So dpdv of your cubic equation of state should become 0, and also the square p and then dv square, that should also become 0 to make it inflection. That's your that's your kind of condition for that inflection point. And then so by using that, so you really take the derivative of the pressure with respect to the volume once and twice, and then you just insert that critical point values, and then we'll give you this equation and then also this equation down here. And then so out of that we can actually find out this formula. Again, there's nothing to be remembered for you, but anyway, this is how we derive it. So out of this information, again, these are the information given. Once you're given substance, you can back calculate what A and then B will be required for your van der Waals equation of state for your certain substance you chose. Okay, so questions about this? 괜찮아요? Yeah. Okay. 네, 감사합니다. 갑시다. Okay. And then here, as I mentioned, so we wanna determine the phase changing pressure at a given temperature. So meaning, in this specific plot, we have at this given temperature, we have this van der Waals curve we have, and then this is not what we want. We want this. So we want that part, phase changing part. So definitely, because when you just draw the constant pressure line across, we need to have two volumes, right? So meaning if I draw the constant pressure lines across, I need to have two volumes, one for liquid, one for gas. That's what's required. Meaning that horizontal line cannot be here. Is that right? Does it make sense? That cannot be phase changing line for the blue isotherm. Is that right? 예. 다시 한번 한국말로 얘기할까요? 예, 그러니까 phase change가 일어난다는 얘기는 결국은 pressure가 constant 할 때, 지금 여기 보시다시피 pressure가 이렇게 constant 할 때, 결국 그 pressure에서 이건 아이소썸이죠. T constant. 이 아이소썸에서 어떻게 된다고? 여기 두 가지의 볼륨이 존재해야 된다고요. 하나는 liquid 볼륨이고 하나는 vapor 볼륨일 거예요. 그렇다 보니까 지금 우리가 지금 요 커브에서 이게 블루 커브를 그렸는데 이 블루 아이소썸에 대해서 우리가 이거 우리 페이즈 체인지 어디서 일어나는 거지 하고서는 프레셔가 컨스턴트한 라인인데 하고선 지금 여기다 보시다시피 요런 이거 레드 라인을 그려버리면 저기는 이 지금 그렸던 블루 커버가 만나는 게 한 점뿐이 없잖아요. 볼륨이 하나뿐이 없잖아. 그러니까 저기는 있을 수가 없다는 얘기지. 그러니까 프레셔는 저거보다 분명히 지금 점점 낮아야 되겠죠. 올라가 봐야지 아무런 달라지는 게 없죠. So it should be lower than pressure. And then if you go there, it still has one root, so it's not going to give you the phase change. So meaning you better have your pressure in between this maximum and then this minimum value. So you have that phase changing pressure level, something in between those two pressures. Does it make sense? 이해가요? Okay. 좋습니다. Okay, then now we need to determine where in that region we should put that pressure line for your phase change. That's what we try to determine. Okay, that's what we try to do. Okay, so to do that, let me just delete this off. Okay, so if we have two phase, liquid and then vapor, you have liquid here and then a vapor there. So they're in phase equilibrium. So phase equilibrium is one of the kind of the thermodynamic equilibrium. So what are those conditions for the thermodynamic equilibrium? What are those conditions for the thermodynamic equilibrium? What are those three equilibriums you need to meet? Or you can just say in properties. What should be the same between these two phases? What should be uniform in thermodynamic equilibrium? TP. Okay, that's good. And then one more thing. 뭐 쓸 수 없었고 쓴 건가요? 아니면 실제로 V를 쓴 건가요? specific volume은 아니기는 하고요. So you remember we have the thermal equilibrium, mechanical equilibrium, and then what is the final one? Chemical equilibrium. Do you remember? Yes, very good. So you have the chemical equilibrium to be met. Okay, so thermal equilibrium requires what should be the same for the thermal equilibrium? Very good. Okay, very good. And then you have mechanical. What should be the same? Okay, good. Okay, you have pressure. And then finally, you have chemical. Do you know what it is? What should be uniform for the chemical equilibrium? Concentration, very good. But in this case, it doesn't help. It's not really the concentration. We're going to come back to the point. But anyway, the concentration, that's actually how I say it in first thermal, because you don't know the chemical potential, but you're going to know the chemical potential in this semester. But let me say, I'm going to tell you, and chemical equilibrium, you should have chemical potential uniform throughout. Meaning your temperature of your vapor and pressure of your vapor and the chemical potential of your vapor of your water, for example, should be individually equal to temperature in the liquid phase, pressure in the liquid phase, and then chemical potential of your water in the liquid phase, and then they should be the same with the chemical potential of your vapor water. So that's that thermodynamic equilibrium or phase equilibrium. So because we already chose in this isothermal line, we already chose the isothermal line, meaning we are at constant temperature for both phase wherever you are. So meaning temperature is already at equilibrium. And also we're trying to draw the horizontal lines, meaning we fix the pressure for the end-to-end points, meaning your two phase will have the same pressure we are enforcing it. So meaning T and P are already at equilibrium. That's what we're trying to find. And then now the last one is the chemical equilibrium, which we need to find out. So in chemical equilibrium, and then the chemical potential of your substance in liquid should be the same with chemical potential of that substance in vapor phase. That's what's required. Okay, and then if we have, so just to be, simple enough, and if you have pure substance like that, just water you have there, or oxygen over there, so not mixture, and then for pure substance, chemical potential can be simply expressed by the Gibbs equation. Okay, the Gibbs equation, and then you remember what the Gibbs equation? Gibbs function, not Gibbs equation. What am I saying? Okay. Do you know what that Gibbs function is? Gibbs function. Gibbs energy. No. Okay. H minus Ts. Okay. Okay. Very good. Very good. Very good. You know that. Okay. So yeah, H minus Ts, or as you say, H is your U plus PV minus Ts. That's your Gibbs function. So your Gibbs function in vapor phase is equal to Gibbs function in liquid phase of your pure substance. Okay, and which is this guy. Okay, that being equal, and then down here, what you write down here is this F is your Helmholtz. So again, this is your Gibbs function, or Gibbs energy, doesn't matter. And then this F over here is Helmholtz energy, well, Helmholtz function. Do you know what that is? Okay, okay, very good, very good. Okay, very good. So that's your U minus Ts, as you say. So U minus Ts. That's your Helmholtz function or energy. Okay. So you have a Gibbs function and a Helmholtz function there. So meaning this Gibbs function, so you understand this equation, and then now you can derive this equation because Gibbs function and Helmholtz function has the, as you can see, the F plus PV is equal to G, as we written down in these two equations. Okay, so we can just write down this second equation. And then we can just kind of move a little around, and then we have this pressure, because pressure is constant when you're considering these 2 points. So we just gonna get the pressure out of the equation, and then it's like that, which is given by this. Okay. Any questions so far? 혹시 여기까지 괜찮아요? 미안해, 이거 지금 쓰는 데가 좀 복잡스럽긴 한데 이거 왔다 갔다 하기가 조금 어려워서 일단 그냥 이거 보고 할게요. 괜찮아요? 여기까지? 오케이. 예. 좋습니다. 그러면은 제가 다시 이쪽을 좀 지우고 쓸게요. 네. Okay. All right then. Then the left-hand side here is quite obvious. You have pressure, and then the V sub B, and then V sub D is actually, that's what I want to determine. So I have that point. Once I draw that horizontal pressure line, if I draw the horizontal pressure line, this is your VD, and then this is your VB. So this is all you know. Okay. This is all you know. Okay, but the right hand side, this is not obvious as is. So what are we trying to use? We are trying to use the Gibbs equation. I think that you remember the Gibbs equation in this way: TdS is equal to du plus pdv, right? Is it familiar to you? That Gibbs equation? 이거 Gibbs equation 기억나시죠? 뭔가 본 적 있는 것 같죠? 네, 그럼 다행이고요. Okay, so let me tell you, because I like Gibbs equation, and the Gibbs equation is one of the most important and which is one of the well-used equation in thermodynamics if I choose one. Okay, so please remember that. And then if you just write down this equation for your energy or thermodynamic potential, we call energy, and then this will look like that. And actually, you can convert that Gibbs equation for the Helmholtz function here, so dF, and then I'm not going to do it. We're going to do that later on when we deal with the thermodynamic potential. But for now, it'll just give you, this form, which is Gibbs equation for your Helmholtz function. Okay. So again, for now, anything here doesn't need to be remembered. Just kind of follow the logic, and then that's enough. Okay, so meaning your Helmholtz, the change in your Helmholtz energy dF is given by the right hand side like that. So, and then this is what it's trying to understand, what it's trying to calculate. So what is the Helmholtz energy change from D to B? That's what it's trying to get. So we can use this formula here to calculate the FB minus FD by integrating the right hand side. That's what you're gonna do. So meaning so to calculate FD to FB, and then we're gonna just simply integrate the dF, and then by using Gibbs equation, we can just integrate from D to B of SDT minus PdV. Does it make sense? 이해가세요? 네, 그렇죠? Okay. So, and then we are on that isotherms when we integrate this right-hand side. So we are integrating from D to B on that isotherm. What happened to this first term over there? Very good. That's simply 0 because there's no temperature change along that curve of that cubic equation of state, because that's that isothermal lines. So this one is gone. In your integration, you simply left with this second guy. So meaning now you understand this final equation over there. Does it make sense? 괜찮아요? Okay, very good. Okay then. So you have this equation which tells you the FB minus FD, and then FB minus FD was here. So you can just plug that right-hand side, this right-hand side, and then to there. It's getting dirty. But anyway, so you just kind of put that over there, and then finally your equation is this. Okay? So let's try to understand the equation. So the left-hand side of the equation, this guy. So if you choose this as your phase changing pressure, and then what that tells you is what? What is that? P times VB minus VD. Okay, so I know it's hard to say because it's actually the area. So is that okay? Yeah, you have a way to saying it. So this is actually the rectangle. But anyway, you're right. That's that area. Does it make sense? That's the left-hand side. And then right hand side, you know where I'm getting at. So this right hand side is the PDV integration on that isotherm of your van der Waals equation of state, meaning you're starting from here, and then your function, pressure function as a function of V, look like this up to that point. So meaning that integration is the area under that blue curve. And then what that equation tells you, those two areas, so meaning it's hard to draw, but anyway, I know you got the sense. So those blue and red areas should be equal to each other. That's what's required. And then what should be true for this area down here, and then this area over there? What should be true? They should be equal and then opposite each other to make that whole area becomes that rectangular area. Is that right? 이거 이해가시나요? Okay, so sorry about all this kind of mess around here, but anyway, I think you got this. You got what it is. So meaning, if you just choose the right pressure line over there, you can make that kind of those two black areas kind of become the same area, and then in that pressure, that's your phase changing area, and then finally this VD and then this VB is your saturated liquid and saturated vapors specific volume you try to find. And then that's Maxwell equal area rule is called. Question about it? 뭐 충분히 이해하신 것 같으니까 넘어갑시다. Okay, so and then here we just try to make it more complex, but not talking anymore about the equation of state, but it still is about the PVT relationship. But PVT relationship not given in a functional form, but given in surface. Okay, so this three-dimensional surface. So I'm saying surface because I don't care what below, what above. So the surface, really, the surface here, not under it, not over it, that surface. So think of it as a mountain, and the mountain surface is your equilibrium state. That's where your substance resides at in equilibrium condition. Okay, so meaning equilibrium state doesn't reside under or above this mountain surface. Okay, it should be clear. So this picture or this 3D, this 3D figure gives you the PVT surfaces for your real substances, how they reside in. Okay, that's the first thing I need to point out. And then the second thing, this is the pressure, volume, temperature axis, so PVT. And then so far we've talked about PV diagrams. So we are talking about PV diagrams so far. And then how can you extract PV diagram out of that surface? By looking at from this side to that way, right? So by looking at that way, we can, project it, and then we can get PV diagrams. 이거 이해가세요? 이게 좀 막 사실은 이게 처음 보면은 하고 오랜만에 보면은 저도 볼 때마다 처음씩 헷갈려요. 근데 기본적으로는 그 개념은 아시겠죠? 그죠? 이게 PVT surface고 surface 위에 equilibrium state가 존재하는 거고요. 그리고 우리가 PV 다이어그램은 당연히 여기서 저쪽으로 정사형을 시키면, 그러니까 프레셔하고 볼륨만 저쪽으로 정사형을 시키면은 우리 PV 다이어그램 그릴 수 있겠죠? 뭐 이해되십니까? 네, 뭐 다행이네요. Okay then, and then just please try to remember what you've seen in the PV diagram here before, and then try to find out the lines. And then in the PV diagram, remember, we draw the isotherms. So ideal gas like, and then it's just simple monotonic, and then it just going across that critical point, it has an inflection point. And if it's under the critical temperature, it has a phase change. And then that's exactly what's shown on this surface. So all the lines here, so meaning all these lines here, these lines are isotherms. As you can see, it has the perpendicular to the temperature axis. So these are all isothermal lines you're seeing. Okay, so those lines are isotherm. Just bear them in mind. Okay, so and then actually this is okay. I mean the PV diagram, I think the isotherms you already understood. And then in this figure, you also see this plot over here, which is the pressure versus temperature plot. And then it's just going that way, right? I mean, just you know where that way is. Okay, it's going that way, and then you just projecting it. And then now what you see is this. Okay, just make it different color. Okay, this line over here is what? Can you just imagine it before I draw it? And then that's over here and here. Can you see that? From that perspective, those two red lines on this surface, they are actually the one single lines, because you know they're sharing the saturated liquid and vapor, and then they're at the same level. Again, remember all these lines are isotherms, meaning they are all isobar inside of vapor dome. The blue area is a vapor dome, and there's a constant pressure. Constant temperature means constant pressure. So meaning those two red, from this point of view, they're actually being together, and as shown as a single line in this PT plot. 예, 뭐 사실 이런 디테일을 내가 얘기하고 있는 것도 좀 이상하긴 한데 어쨌든 간에 뭐 좀 상상 가세요? 그럴 것 같지 않으세요? 뭐 이해되세요? 아, 예, 뭐 클리어한가 보나. 괜히 저만 걱정 안 해버리네요. Okay, so that's the PT plot. And then as you can see, because there is a critical point here, and then that is actually this critical point here. And then this line, this red line, separates the vapor and liquid, as you've seen in the surface, and then in the PET surface, and then that separate vapor and then liquid phase. Okay, or that's exactly this line over here in this PT. This is the same PT plot, and then this is it, and then this is your critical point. Okay, so this is the TP plot. And then I think we just run out of time. And then is there anything I need to point out? We need to talk about the solid, but I think it's too much. Ooh. Okay, maybe I can just kind of continue on that kind of solid phase, because it's gonna be a somewhat long discussion. So I can stop here for today. 오늘은 그냥 여기까지만 할게요. 사실은 간단하게 하려고 했던데 그냥 얘기하다 보니까 길어진 상황이 좀 돼버린 것 같아서. 혹시 뭐 궁금한 거 있어요? 질문 있어요? 뭐 별로 없어요? 아, 예. 알겠습니다. 그러면은 오늘 뭐 수업 여기까지 하시죠. 예, 수고 많으셨습니다. 예. 예, 감사합니다. 뭐 다음 주 화요일 날 봅시다. 주말 잘 보내시고.